right, welcome back. This chapter again is about continuous distributions or continuous random variables. The difference primarily, and I told one difference last class, but I'll explain it a little bit more here and you'll get to your first distribution, is that whereas for discrete case, x can only be integer values like 0, 1, 2, 3, 4, and so forth, continuous can have decimals in between. So you can have a value like 17.83 years old or 7.12 meters tall, or, so there can be decimals. It doesn't mean that you're recording decimals. It just means that decimals are possible. And what I mean by that is, and I'll use age as a great example. Typically, if someone asks how old you are, you usually just say, oh, I'm 21. Oh, I'm 19. And you don't usually tell them, oh, I am 19.3. At most, you might tell them 19 and a half, you might give a half, but more often than not, people, it's just human nature to report your age to an integer value. Even though you might record integers, the fact that you could have decimals means that it's continuous random variable. So that's an important distinction. It doesn't matter how you record it. It matters, could you have had decimal places? So with that in mind, let's take a look at this first set of details here. You've got some requirements in order for it to be a valid probability function. Whereas for discrete, it was called a probability mass function. Now for continuous, it's known as a probability density function, or PDF. And usually it's written as a lowercase f of x. So it's no longer a capital P of x, it's a function f of x. This function needs to satisfy two criteria. One is that it's always non-negative. So it can't dip below the x-axis, otherwise it's not a bona fide probability function. And the integral must be 1. From calc, I assume it's calc 2 for you guys, what does integral correspond to? What concepts?
Area under the curve.
Area under the curve. So that means that the area under a probability density function or a probability distribution function must be 1. So this is also implying that probabilities and I see that I wrote it here, are areas under the curve. And so you're not adding something, you're looking at the area in a region underneath the curve. Those are your probabilities. And the total area under the curve must be 1 in order for it to be a valid PDF. So it's important to keep in mind as we progress. If you wanted the area in between, let's say, some value A and B, then you're going to integrate from A to B over the f of x function, which is what I have on the next line. There is a well-known distribution function, or a PDF, that is given in the middle here. It is 1 over b minus a. And we're going to talk a bit more about that. This corresponds to what's called the uniform distribution. In general, the uniform, when you think of uniform, you think of all the same. And that's what the uniform distribution looks like. If A is some value here and B is here, then uniform is this horizontal line from A to B. And that's it. It really is that simple. And keeping in mind that the area under this curve has to be 1 for this to be a valid distribution, you think to yourself, okay, well then what is, bless you, what is the height here? and you remember, oh, this is a rectangle or a square, depends on, you know, how good of a sketch you do. And so this is sum f times the width. This is the area, length times width. And that has to be 1, which means that f is 1 over b minus a. So that's where this PDF came from. It's the easiest one that you're going to come across, which is why I start with it. And then we get to some others that are a bit more fun to play with. There is something called a cumulative distribution function, which I'll talk more about later. But this is essentially the integral over the PDF from the first value, the minimum, up to some general x or t value based on how I wrote it there. So it's cumulative because it goes from the beginning up to some value. So it gives you the area up to or less than or equal to whatever t or x value you're interested in. But it's considered a function because you're actually deriving it for any x or t value. So you don't usually plug in right away. And like I said, we'll make use of it a little later on. But let's get to applying this. And our first problem says, let x be the length of time in minutes between 911 calls. Suppose that x follows a distribution with the PDF f of x equals 1/20th e to the negative x over 20, where x is greater than or equal to 0. What is the probability that the time between calls is greater than 20 minutes? So remember that x in the beginning is defined as the length of time between calls. And so we want the probability that x is greater than 20. And I'm getting that right from this bottom line here, the last sentence. So we want the probability that x is greater than 20. The neat thing with continuous is that the sign in the middle between the x and 20 has some flexibility. So having an equal part in there doesn't actually change the problem. So the probability x greater than 20 is exactly the same as the probability x greater than or equal to 20. The answer isn't affected as the discrete distribution would be. But here, being very literal, greater than 20 is strictly greater than, no equality. According to what we saw earlier, this is going from 20 up to infinity, because we know according to the PDF that's given, x is greater than or equal to 0. So we want x greater than 20, which means we're starting at 20 minimum and going upwards. Remember, this is continuous, so it's really 20.00001, but that's so close to 20 that starting at 20 is fine. And f of x is given as 1 over 20 e to the negative x over 20 dx. And this is the integral that we want to evaluate. What is the integral of this function? Before you evaluate, what is the integral?
Negative 20e to the power of negative 1 over 20x.
So I heard negative, you said 20,
To 20.
20e to the negative x over 20, is that what you said?
Yeah.
So almost, I think you had pulled the 1/20th out of the integral, and so it's still actually there. And
Oh,
so
yeah.
that 20 does cancel out, and we've got negative e to the negative x over 20, which you are evaluating from 20 up to infinity. So this is an indefinite integral, which came up probably in Calc 2, I'm guessing. And so we really should have converted to its limit form up front, but I'll make that adjustment here. And so this is the limit as I'll use capital A goes to infinity of negative e to the negative a over 20 minus negative e to the negative 20 over 20. So it's common for students to kind of ignore limits and kind of just plug that infinity in and realize, oh, that's going to be e to a really large negative value, which is 0, but it's the limit is 0. And so it is important to recognize that this first term formally really is a limit, whereas the second term is just a straight up plug. And so when I follow through on the limit, this limit again, as a goes to infinity, that power gets larger and larger, but more negative. So it's like 1 over a really, really large number, which is 0, minus a negative, which is plus, e to the negative 1, which is e to the negative 1. And when you put this into decimal form, I've got 0.3679. This is your first example of how you might use a continuous distribution. Now, this PDF is a well-known one, but I'm introducing it here, but I'm not going to give you its name just yet. We'll get to that maybe next class. But that is a well-known one and a fairly simple one to apply. Let's look at the next problem, problem 2.
I have a question.
Mm-hmm.
Can you go back up to the equation?
What's your question, Sydney?
And so there's two different, there's one where it's like f of x is 1 over b minus a, and then the other one is like.
Well, so this is one type of a distribution. This is called the uniform distribution. But there are many distributions, and a different one was given in example 1. So example 1 didn't use the uniform distribution, it used something else.
Okay.
All right, and problem 2 also uses a different distribution. Let's find out what it is and what we want to do with it. It says determine the cumulative distribution function. So this is the CDF of g of y equals 2y, where y spans from 0 to 1, and use that in order to compute the probability that y is between 1/2 and 3/4. Right, so we need to get our CDF. So the CDF is going to be, typically it's the capital letter of the lowercase one that you used for the PDF. So since we have little g of y, I'm going to call this capital G of y. And based on the definition of CDF, this is the integral from the lower bound up to t. I'm going to write it a little differently because I'm writing the CDF not as a function of t, but as a function of y. So I'm going to write it as 0 up to y of 2t. So I wrote little g of y as g of t. And this is dt, integrated with respect to t. 0 is coming because the support of y was given as 0 to 1. So you start from the lower bound and you're going up to some temporarily unknown value, which is our little y. And we want to evaluate this, which is a polynomial, so you should be thrilled to have an integral like this. Integral of 2t is what?
1/2 t.
What's the integral of t?
T squared over 2.
Oh, yikes.
T squared over 2, yeah. And you have that 2 up front, which is canceling out. And so this
T
is just going to be t
squared.
squared. Now, it's not an indefinite integral, so you don't have to put the plus c in. Even if you did, it would cancel out. But we do want to evaluate this from 0 up to y. So you've got y squared minus 0 squared, which is just y squared. So this is our CDF. Let's get graphical here. That could be fun. Our PDF, g of y equals 2y, is this function here. And this is 0, and this is 1. So it doesn't actually go onwards. It stops. Whoop, it stops at the support. That's our PDF. And then our CDF is y squared, which is this. That's what we see. Those are our two functions that we're working with. And what I want to know is the probability that y is between 1/2 and 3/4. Now, what I know, is that this is the same as the probability that y is less than 3/4 minus the probability that y is less than 1/2. So it's just another way of viewing that probability of the area between two values is the same as the area below or to the left of the larger value, and then subtract off the piece of the area that's to the left of the smaller value. And what's left is the area in the middle. If you have trouble viewing that or visualizing it, let me do a quick sketch here. So we want the area in between these two lines. The first probability, the probability y less than 3/4, is giving us all of this. The second probability, y less than 1/2, is removing this area. And what's left is going to be that middle piece with only horizontal lines in it, which is exactly the area that we want. Now, what's neat about having a CDF, which isn't always required, sometimes you could skip getting a CDF like we did in Prop 1, but what's neat about it, if you have it, is that it could give you these less than probabilities right away. And so the probability that y is less than 3/4 is capital G evaluated 3/4 minus the next probability is capital G evaluated 1/2. And we know that capital G is y squared, which means this is 9/16 minus 1/2 squared, which is 1/4. And so that 1/4 is 4/16, which means we have 5/16 as the area in between or in the middle of that region. Having gone through 2 problems so far, any questions at this point?
Wait, what about the, you know, the part where the CDF is what, the 1 over b minus a or something?
Oh, you're back at the beginning?
Yeah.
What is your question? Because we haven't made use of that yet.
Oh, because isn't it equal to, well, when do you use 1 over b minus a? Because you didn't use it for this one, right?
No,
Even though that
I
was-
will let you know. We're almost ready to make use of that. We're not quite there. We're not using a uniform distribution just yet. Let's look at problem 3, where a non-uniform distribution PDF is given. F of x equals sum c times the square root of x. This is a PDF with support x being between 0 and 4. And we want to know what must the value of c be for this function to be a PDF. So I look back here at the 2 criteria. And for the first one, I realize, okay, well, I need f of x to be positive. And when x spans 0 to 4, I know that x is not going to be negative. So in order for number 1 to hold, c must be a positive value. Right, so I know that whatever my answer is, it has to be positive. Now, the second one, the second criteria says that the integral over the support has to be 1. So the total area under the curve must be 1. So I go back here and I look at per number 2, the integral from 0 to 4 of c root x, which is x to the 1/2 power. This must be 1. And so when I actually evaluate this integral, the integral of x to the 1/2 is going to be x to the 3/2 divided by 3/2, which is 2/3 cx to 3/2 evaluated from 0 to 4. So that is 2c over 3. And if plugging 4 in, I've got the square root is 2, and then cubed is 8. Minus, when I plug 0 in, square root of 0 is 0, cubed is still 0. So I've got 16c over 3, this must be 1 for this to be a valid distribution, which implies that C has to be 3/16. And as a quick check, it satisfies the first line, which is I knew that C must be positive, 3/16 is positive, and so both of our criteria are satisfied, and that is going to make it a valid probability density function. Now, problem 4 gets to actually using the uniform distribution. So just before we start on that one, any questions on anything from problems 1 through 3?
Wait, what
All
is
good.
the PER 1 and 2 again?
Oh, per?
Yeah.
Those are the criteria at the top of the page. So for it to be a valid PDF, f of x must be greater than or equal to 0 for all x, and the area under the curve has to be 1.
Wait, and this is uniform distribution?
No, it doesn't have to be. This is true for every PDF, not just the uniform.
Wait, number 3 is uniform, though.
No, I said number 4, which we were about to get to, is uniform. We haven't made
Okay.
use of the uniform distribution at all. It sounded like someone else was also going to ask a question. I'm not sure who it was though. Did anyone else have a question? Okay, well, let's take a look at problem 4 then. It says, let X have the distribution uniform from 0 to 100. We want to determine the following probabilities. So uniform 0 to 100, a quick sketch. Looks like that. And according to the f of x boxed out up here, we know that the height of that horizontal line is going to be 1 over b minus a, where b is 100 and a is 0, which means this height is 1 over 100. And so again, remembering the formula is fine, or just thinking through it logically. This is a rectangle, so you have to have a height such that the height times the length, or length times whichever perspective you like, is going to give you an area of 1. We want, for part A, the probability that x is less than 28. And so 28, I'll say, is here. So for part A, it's asking, what is the area of this region? And you could get this geometrically, or you could get it from integration, and we'll do it both ways so that you see that they work for the uniform distribution. Uniform is really easy because it has a simple geometric interpretation, but other distributions which aren't squares or rectangles are a bit more obscure. And so geometrically, you look at this and you say, okay, well, the length of this shape has a base of 28 and a height of 100. And so that's going to give me 28 over 100, or 0.28. And that's right. But let's go through and actually use integration. So this probability is the integral from 0 to 28 of the PDF or f of x function, which we got to be 1 over 100 dx. When you integrate this constant, you've got 1 over 100 times x evaluated from 0 to 28, which is 1 over 100 times 28 minus 0, which gives you 0.28. So both approaches work. Integration, more often than not, is what you're going to have to use for most continuous distributions. But I like starting off with this one just because you can get it more geometrically. So if your integration isn't where it should be, it's nice to be able to check it from a geometric perspective. With that being said, I want you to try to do B, C, and D. And while attacking it geometrically is fine, at least one of them also try to do with integration just to be sure that you can apply it. And so I'm going to give you a few minutes to tackle those 3 parts. And again, at least one of them do with integration too. Right? And I'll return in a few minutes with that. All right, so it's been almost 5 minutes. If you have an answer for part B, feel free to call it out, or again, you could post to the chat board.
.35.
Yeah, so same. Great. I'll just go through it just to make sure that those that may not have gotten that see where it comes from. And I'll do it from the integration approach, but you could always create a sketch kind of like I did in part A. You would just shade in from 0 or from 65 up to 100. So make sure you're shading in the correct region. This is the integral from 65 to 100 of 1 over 100 dx, which is going to be 1 over 100 x evaluated from 65 to 100, which is 1 over 100 times 100 minus 65. And that's going to be 35 over 100 or 0.35. So that is the integration approach to answering this one. But again, it should match the geometric one if you happen to have done it that way. What about C? Anyone get an answer for C?
I don't know if I did it correctly, but I got 0.18.
That is correct. Oh, okay, yeah, there's a few other posts. And good job, guys, or guy and girl. Let's see, so to do this one, again, you could do it geometrically or integration. Let's go with the geometric one for this perspective. This is going from 15 to 33, and I realize I'm not quite to scale, but you get the general idea. And we want this region here. I know the height of this line is 100, and so the area, which is the probability, is going to be the height, which is 1/100th, times the width or the length, which is 33 minus 15. And that difference is 18. So 18 over 100 is 0.18, or 18%. And then you get to part D, which has a little trick in it, but anyone feel that they've got it?
0.97.
That isn't quite. I'm not quite sure where that's coming from, but Nick, yeah, it looks like you got it. And so, Nick, I assume you go by Kiko since you're putting the quotes in
Yeah,
there.
either one is fine.
Why 0.1? What did you realize didn't matter?
The area under, well, the 100 to 107 is 0 because the curve stops there. So you just integrate from 90 to 100.
Perfect. So for us, the distribution, and I'll highlight it just to kind of make it stand out. Your PDF is really like this. I tend not to emphasize the parts outside of the region, but the probability beyond, below 0 or above 100 is 0. And so the focus is really on the area under the non-zero curve, or between 0 and 100. And so what we're looking at here is just from 90 to 100, which is that region there, which is going to be 0.1. This one I'll do through integration, and Kiko had described it. This is integrating from 90 to 100 because the PDF after 100 is 0. Right? And so the PDF before 100, between 0 and 100, is 1/100th. The x, when you integrate this, you've got 1/100th x evaluate from 90 to 100, which is 100 minus 90. And that's 10 over 100, or 0.1, or 10%. Yeah, that's one that, a lot of students will miss that, but that's why I put it on here, so that you will have seen it prior to homework or a quiz or something. But it's important to keep in mind, what is your support?
Wait, miss what?
Sorry?
What did you say people miss?
Miss the fact that this is asking for the area between 90 and 107, but the area between 100 and 107 is 0. So you don't have to actually consider that region.
Between, wait, what's 0? Sorry.
We're really looking in this entire region, but the area in this region here from 100 to 107 is 0, because the PDF is 0 in that region.
Wait, why 107?
Because that's what the problem says. The probability that x is between 90 and 100.
Oh, sorry, no. Sorry, I meant. So why is it 0? Because you said the PDF is 0, but like, is it because it ends at 100?
Well, we know that it has a non-zero height or curve between 0 and 100. We know that the whole 100% of the area is between 0 and 100, which means that the area outside of that interval has to be 0. And the only way for that to be true is for the PDF to be 0, or those thick black lines on the x-axis above 100 and below 0. You see the regions that I'm talking about? I kind of put a little yellow about them now just to make them stand out.
Wait, because so they're after the area, right?
Hmm?
So that's why they're 0?
Hmm? Yeah, because if they were anything but 0, then you'd have more than 100% under the curve, which would not make it a valid probability density function. Sydney, does your silence mean you got it?
Yeah, I'm just copying it. I think
Okay.
I basically get it.
And that's all of the problems on this handout. Any questions before we move on to another one?
All good.
All right. Sydney, did you copy it all down?
Almost.
All right, let me know when I could switch.
Oh, I have a quick question.
Hmm?
So, is there like any particular series we have to like, I guess, remember for this whole course? Like besides you know, like what we learned so far?
I don't think so. You're just thinking about what's coming up. I don't think series are going to play a major role. I mean, most of series has come up already with discrete, like geometric. But you don't have to refresh your memory on telescoping and harmonic, unless you just want to do it for fun, but it's not, it's not going to be a big part of the course at all.
So will we have to, I guess, expect to use series on like the quizzes and exams later on, or it's fine if you just don't know them at all?
Well, no, it's helpful to at least know the geometric one that we've made use of a few times now.
Right.
Like 1 + r + r² + r cubed, that one.
Oh yeah, that wasn't too bad.
Yeah. I mean, I'm hesitant to say that that's the only one. I think it is, but I just may be forgetting another instance coming up. But I think that will be the prominent one.
Okay. Hopefully that comes up soon. So.
Well, you've already seen it, so it already came up. I don't believe it comes up in continuous.
All right.
And I can't think of another reappearance, but I just may be forgetting.
Okay. Thanks.
You're welcome. Sydney, are you done?
Yeah.
All right. All right, so that was your little intro to continuous distributions, just kind of got you finding probabilities using some continuous PDFs, and you had a CDF example there. This handout, the next topic, is going through expected value and moment generating functions, but now using continuous distributions. This table summarizes the relationships. You can see that the discrete part you had already learned, and the continuous part looks very similar. The biggest change is that the summation, the capital sigma, is replaced with an integral. And that's really what it comes down to. So if you want the expected value of some function u, in the discrete case, you would sum every u times p product. In the continuous case, you will get the area under the curve of u times f. If you want the MGF, which is still the expected value of e to the tx, so I'm looking in this box here. If you want the MGF, which is the expected value of e to the tx, in the discrete case, you summed up every product of e to the tx times p. Sometimes you used a trick in order to evaluate that. In the continuous case, you would integrate the e to the tx times f. So that's, the process is similar. Now you just have a slight tweak in the formulas for the continuous scenario. So let's go ahead and practice it just so you could actually see it applied. In part 1, it says use mathematical expectation to find the mean and variance of a uniform distribution from A to B. So because it's uniform, we know that f of x is 1 over b minus a, where x has the support of spanning a to b. All right, so that's just given. It's not something I derived or created. We know it's a uniform distribution from a to b, and that's how I know this is the PDF or f of x function for it. The mathematical expectation. So here we want the expected value of x. Remember, this is the mean. And because uniform is continuous, this is going to be the integral of x times f of x, which is 1 over b minus a. And this is over the full support of a to b. So those are your bounds of integration. 1 over b minus a is constant with respect to x. So this integral is the same as 1 over b minus a times the integral of x dx, integral going from a to b. And so x is, when you integrate that, becomes x squared over 2. So we've got x squared over 2 times b minus a. That's all in the denominator. And this is being evaluated from a to b, which is b squared minus a squared over 2b minus a. And while it may feel like there's nothing left to do, you can actually simplify in this one because the numerator factors into a b minus a and a b plus a. Which enables us to cancel out the b minus a on top and bottom. And so our answer is that the mean is b plus a, or you could write a plus b, both ways are fine, over 2. So that's our mean. Now we need to go through the process of finding the variance. Variance isn't especially different. We need the second moment, so we need the expected value of x squared, which is the integral from a to b of x squared times 1 over b minus a. This is going to be x cubed over 3b minus a, which again, you are evaluating from a to b. And so when you do that, you've got b cubed minus a cubed over 3b minus a. And then from here, I would look to see if I could factor that b cubed minus a cubed into a b minus a times something factorization. So let's do that over here. So I look at this and I say, okay, I'm going to do long division. So b minus a going into b cubed, I know that's going to be a b squared. When I multiply through, this gives me a b cubed minus a b squared. I want to subtract this from above. The b cubes disappear, and I've got a b squared minus a cubed. I look, b goes into ab squared, ab times. So I multiply through, and I've got ab squared minus a squared b. And I want to subtract this line from above. So my AB squares disappear and I've got a squared b minus a cubed. And I realize that b minus a goes into the first term, a squared times, and this gives me a squared b minus a cubed. Subtract this from above, and I get a remainder of 0, which means that this is b squared plus a b squared. I think it was just ab, yeah. Plus ab plus a squared over 3. That is our second moment. Can someone remind me again, how do you get the variance?
Subtract mu squared.
Perfect.
Yeah.
And so this is the second moment, which we just got to be b squared plus ab plus a squared over 3 minus the square of the mean. And the mean is b plus a over 2, but we're going to square that. So that's going to be b squared plus 2ab plus a squared over 4. Now I know I jumped ahead to squaring that in my head, but if you're not going to remember that in your notes, please write down, where that term came from. That is b plus a over 2 quantity squared. And then from here, we want to get a common denominator and simplify. So I'm going to use 12, which means we have 4b squares plus 4abs plus 4a squares minus 3b squares minus 6abs minus 3a squares. So I've got 4b squares minus 3b squares, which is 1b squared. I have 4abs minus 6abs, which is minus 2abs. And I have 4a squares minus 3a squares, which is plus a squared over 12. And that numerator factors into b minus a squared over 12. That is your mean and variance for a uniform distribution from A to B. And so now you could jump right ahead and just make use of these. For example, I'm going to go back to the previous handout. For this uniform distribution from 0 to 100, if we had been asked to find the mean and variance for this distribution, now we could jump right ahead and we could realize, okay, well, the mean is b plus a over 2 or 50. And the variance is b minus a squared over 12. Which is 10,000 over 12, which I don't think that comes out to an especially nice number, but let's see. $833.333. And so now we've got our mean and variance for this distribution. And so it's based on those formulas and it holds for every A-B combination. A is always going to be less than B, so always keep that in mind. So this form is uniform from the lower bound A up to the upper bound B. And that is the standard notation for a uniform A to B distribution. In the next part 2, it asks us to derive the MGF for this general uniform distribution. So let's go ahead and jump to that one. This is, let's see, M of t, by definition, is the integral e to the tx times the PDF of 1 over b minus a dx. And this is integrating from a to b. The 1 over b minus a, again, is constant with respect to x, so I'm going to pull that out. And now we just want to integrate an exponential, which we did last handout. And so we're doing the same thing here. This is integrating with respect to x. So this is going to be a 1 over b minus a. The integral is going to be 1 over t e to the tx, evaluating x from a to b. And I'll emphasize that by writing x equals a up to b. So we have e to the bt minus e to the at all over t times b minus a. And that's it. There's nothing more that we could do with this. That's as simple as we're going to get it. And this holds for every uniform A to B distribution. So just to apply it to, again, the problem in our last handout. Here, our MGF is going to be e to the 100t minus e to the 0t, which is 1, over t times 100 minus 0, which is 100. And that would be our MGF for the distribution problem 4 for this handout. Again, this stuff it's not asked for on this handout. I'm just, using the opportunity to demonstrate it a bit more than what is on the handout. So that's it. We've determined the MGF. It doesn't have us make use of it here. Let's take a look at 3. So in 3, we've got a random variable x with a PDF f of x equals c times 1 minus x. X ranges from 0 to 1. In part A, you want to determine the value of c that would make this a valid distribution. In part B, you're going to want a probability. And part C, you're going to want to use expected value in order to find the mean and the variance. So I want to give you a few minutes here to see how far you can get. I'd like to think that you can do A and B because we've done comparable ideas. And hopefully you're able to do C, but I want to see how far you can make it. So again, I'm going to pause the video and I'm going to give you a few minutes to try to make progress on your own for problem 3. At least A, B, and C. If you happen to finish that early before I restart, feel free to try to tackle D also. All right, so I'm restarting the recording, as you guys already heard. I'm just going to reiterate parts A and B because I neglected to start the recording when I had gone over those. So for A, we want to determine the value of C that would make this a valid distribution. We know that 1 minus x is going to be positive on the support of 0 to 1. So C has to be positive, which is given by the first criteria for a continuous PDF. And then using the second criteria, which is that the area under the curve must be 1, we ended up integrating. We got C over 2 has to be 1, which means C has to be 2. For part B, now that we know the value for C, so we have the complete PDF defined, we want the probability that x is less than a third, which is the area underneath the curve underneath 1/3 or 0 to 1/3. And so integrating 2 times 1 minus x from 0 to 1/3 simplifies to 5/9. We're working on part C, which a number of you got 1/3 to be the mean. So let's go ahead and do that. And you could either check your work, or if you know that you already got the answer, feel free to try tackling the mean if you haven't done so already. So the mean is the expected value of x, which by definition is the integral of x times 2 times 1 minus x. And this is over the full support from 0 to 1. When we integrate this, we've got 2x, which is integrated to x squared. And x squared becomes 1/3 x cubed. Evaluating this from 0 to 1, we've got 1 minus 0 is 1, minus 1/3 times another 1 minus 0. Let me just make sure I didn't lose it. Oh, I lost the 2. That should be a 2/3 x cubed. And so we have 1 minus 2/3, which is 1/3, which is what all of you were saying. So great. And so now we need to get the variance. The variance uses the mean, but it also uses the second moment. So hopefully for those of you that made it past this part, you started tackling that one. The expected value of x squared is the second moment. So this is the integral from 0 to 1 of x squared times 2 minus 2x, or 2 times 1 minus x. And so this is going to be 2x squared, which becomes 2x cubed over 3, or 2/3 x cubed, minus, you've got 2x cubed, which becomes 2x to the 4th over 4, or 1/2 x to the 4th. And evaluating this from 0 to 1, we've got 2/3 minus 1/2. And with a common denominator of 6, this is going to be 4 minus 3, or 1/6. So this is the second moment, which means that the variance is the second moment minus the square of the first moment. And that is 1/3 squared, or 1/9. So common denominator of 18. For 6, that's going to be 3 minus 2, or 1/18. And that is our variance. Did anyone happen to get that before I just went through it? Or did anyone get the second moment? Let me ask that. Marissa, were you at least on the right track of setting it up? Do you understand the setup now, having seen it? Okay, good. And I see that a few of you did at least progress appropriately. So that's great at this point. No problem. You are very welcome. And there is one part left, and that is to generate the MGF, or moment generating function of X. We're still sticking with the same distribution for this problem. And so I know that you may not have gotten to this point. So, well, you tell me, do you want some time to try to do it on your own, or you want me to just progress through part D? Okay. Well, Tim voted first. I don't see any others. So I'm going to pause the video again, give you a few minutes. We've got about 15. I'll see how you're doing at 5, and then I'll return, and of course we'll finish this off before the end of today's class. Okay, so we are continuing with the last problem on this handout, which is to find the MGF of the PDF 2 times 1 minus x. And by first principles, we want m of t, which is the integral from 0 to 1, because that's the support of this particular PDF, e to the tx times 2 times 1 minus x, which I'm going to rewrite this as 2 times the integral 0 to 1 of e to the tx minus 2 times the integral of x e to the tx, and there's a dx in both of these. So we want to evaluate both of these integrals. The first one we've done before, so you should get at this pretty quickly. This is going to be 2 over t e to the tx, which again, we're going to evaluate x from 0 to 1, minus 2.
I have a question.
Hmm?
I don't know if I did it right. Or if it's another way. But you know the part where it's e to the tx times 2 times 1 minus x?
Hmm?
I put 2 on the outside, and I distributed e to the tx with 1 minus x. I don't know if that's right now.
That's exactly what I did, Sydney. So if yours looks like mine,
Wait.
then it's right.
Oh, it looked like you split it up, that's why, because I didn't split it up.
Oh, you left it under one integral. That's fine. I separated just because the integral of e to the tx can be solved with u substitution, whereas the integral of x e to the tx is going to use a different method that'll use integration by parts. Or are you guys taught the tabular method? Does that name ring a bell?
No.
Okay, well, I'll show it to you. It's an alternative way of doing integration by parts. And the way it works, integration by parts requires a u and a dv term. And so u is typically the term that as you take its derivatives, it goes to 1 and 0. And so that's going to be the x part for the second integral here. Derivative of x is 1, derivative of 1 is 0. And when you get to 0, you stop. The dv part is going to be everything else. So this is the e to the tx. And so whereas you took the derivatives, dv, you take the integrals. So the integral of e to the tx is 1 over t e to the tx. The integral of that is 1 over t squared e to the tx. And then what you do is you want to multiply the diagonals. But the first diagonal you keep positive, so you multiply by a positive 1, whereas the second one you multiply by a negative. And if you had more, if you needed more, it would alternate. So positive, negative, positive, negative, positive, negative, as many times as you need. So what that tells me is that this second integral is going to be x times 1 over t e to the tx. And then you've got a minus sign times, or with a 1 times 1 over t squared e to the tx. And this is also evaluated from 0 to 1. So this is an alternative to integration by parts. You're welcome to use integration by parts to see that this is the answer that you would get. It's a nice shortcut, at least some people find it easier to use. So again, this, I think it's commonly referred to as the tabular method. And this is for integration by parts, which I'll just abbreviate as IBP. And so we're evaluating x, not t, x at from 0 to 1. So we're going to get 2 over t e to the tx at 1 is e to the t minus e to the 0 is 1 minus 2. And now evaluating the second parentheses at 1 is going to be 1 over t e to the t minus 1 over t squared e to the t minus, now evaluate the parentheses at 0, and you're going to get 0 minus 1 over t squared e to the 0, which is 1. And now we keep simplifying, but x has disappeared at this point. And so we've got 2 over t e to the t minus 2 over t minus, now I'm distributing the 2 through the second part. So we've got 2 over t e to the t plus, because that 2 is negative, is negated, 2 over t squared e to the t minus, because it's negative 2 times the negative outside the parentheses times the negative inside the parentheses, so minus 2 over t squared. And I see that 2 over t e to the t is added and subtracted here, so it simplifies a little bit. And then you could do what, who was it, Nick? Tim, it was Tim. So Tim got a common denominator. This isn't a required step, but it's not a bad one, of t squared. And so he saw he has a negative 2t plus 2 e to the t minus 2, which is over your t squared. And this is your MGF, which if you wanted, and it would be good practice, you could take the first and second derivatives, evaluate 0, use the second minus the first squared in order to get your mean and your variance, and make sure that you get the same numbers that you got in part C. And that's it. We finished perfectly on time. Any last minute questions?
Wait, so you have to use integration by parts for this?
Well, don't you? You could use the tabular method if you know it, but if you don't, then what other approach do you have to evaluate the integral?
Oh no, I'm just asking. I
Yeah,
guess I didn't get to that.
Yeah, so integration by parts for the second integral that, I mean, I split it into two. So for the second one, you would need to use that. Anyone else with questions?
Wait, is there a,
All right, here are people starting to leave, which is fine. I just want to wish you all a great next few days, and I will see you again on Thursday. You're welcome to hang out if you have questions or you just want to listen, but that is it for today's lecture. It's fair game none. So, you know, the syllabus says any current or past material that's come up, you know, in homework or worksheets or lectures. So, so these two handouts in this continuous chapter are fair game.
wait, wait for the quiz or something?
Yeah, Nan was asking if this is something that might show up on a quiz. You're all welcome.